Hi, this is Kavya, and this is my lab 5 for physics, and I did dropping a slinky. The purpose of this lab is to create an experimental model of a slinky dropping to analyze the motion and compare this movement to a computational model to analyze the forces at play when an object is falling. It also demonstrates the tension within the slinky. The fundamental concepts are net force because the slinky falling has a downward force by gravity, but it is balanced by an upward tension force, causing the net force of the slinky to be zero until the tension force no longer applies and the object falling doesn't have the force to cancel it out. Thus, the velocity is not constant and causes acceleration. It also uses Newton's second law because the system's change in momentum is proportional to the forces being applied on the object, and the acceleration changes throughout the system as the force changes because the forces and acceleration are proportional. We use the equations of Newton's second law, so F naught equals delta P over delta T, and also the velocity and position update formulas. We have the equation for drag force, and then also the force of gravity and the force of the tension, which works in the opposite direction of gravity. In the experiment, the system is the falling object, in case the slinky, and the surroundings are the external forces, so gravitational force and drag force. The initial conditions are time is 0 seconds, the position is -0.5 and -1 meters, the velocity is 0, and then the mass of the slinky is 0.453 kilograms. And the main result of the lab is that the forces that are in play when dropping a slinky change throughout. So when you let go of the slinky, gravity begins to act on each part of it differently because of the tension in the slinky. So the forces do not act uniformly across the slinky, making the base stationary until the top of the slinky reaches the base. So the procedure is to get a clip of dropping a slinky, and I used the one from the internet, and then use Tracker to find an observed model, a code to find the computational model, and then graph them to compare it. So from Tracker, I tracked the video, as you can see, and then you get that two different slopes throughout. So the bottom of the slinky has a constant position at about 0 while being dropped until the top of the slinky reaches the bottom at t equals 0.034 seconds, and then the slope becomes about -8.7x. So for the code, you can see that we have the initial position of the ball, or the initial conditions of the ball. So the mass is 0.45, the initial position, and then the initial velocity you put in, and then we put in the gravity and then the drag constant as well. And then in the computational model, we did 2 loops, one for when the position was constant, and then one for when the position changed, when the top of the slinky caught up to the bottom. And then through that, we got this image of the graph, which we could then put into sheets and then compare it with the observed position. And as you can see, it's pretty accurate with the computational versus the observed, with some offsetting, which these sources of error could be due to other forces in our everyday system. There are forces at play that we didn't account for, as well as inconsistent tracking. While using Tracker, there might be slight changes in the real position. So the acceleration of different parts of the slinky depend on the net force acting on each part. The top accelerates immediately due to gravity, and then the bottom stays momentarily stationary because its net force is 0, because the upward tension equals the downward gravity. And once the net force on the bottom becomes downward after the wave reaches it, it begins to accelerate downward. So if you consider a slinky as a whole, its center of mass falls with a constant acceleration 9.8 meters per second downwards from the moment it's released due to the net gravitational force acting on the slinky. So the top moves down initially, and the bottom catches up once the center of mass moves uniformly downward according to the gravitational force on the slinky's total mass. So if the slinky were twice the length, the same fundamental principles would still apply, but there would be some noticeable differences. The center of mass of the slinky still falls at the rate of gravitational acceleration regardless of its length, but with a longer slinky, it would take more time for this wave to reach the bottom of the slinky since the wave must travel at a greatest distance. As a result, the bottom of the slinky would stay stationary for a longer period before it begins to fall. Thank you.